Okay, so this is the third lecture in the series on coherent groups by Danny Weiss, and very happy to have.
Okay, thank you so much. All right, so in case I forget to say at the end, it's been a pleasure to be here and very gracefully hosted, and nice to see people awake. I hope that you'll get relaxed from this talk and you'll emerge well rested. Okay, so I'm going to talk about coherence. So a group G is coherent if every finitely generated, I'll write it out just this one time, finitely generated subgroup is actually finitely presented. Meaning, so finitely generated, means you have a finite subset that isn't contained in that every element can be expressed as a product of those and their inverses, for instance. And finitely presented is a little harder. It means that it has a finite presentation, right? So finite presentation means you might have a few words expressed in the generators, and your subgroup H is isomorphic to the group that is given by this presentation. So this is notation. I don't know, what people are comfortable with. This is notation for the quotient of a free group. I'll write it like this: the free group generated by A, B, and C by the normal closure of these elements, which are called relators. Okay? Okay, so, all right. So, what are let's list examples of coherent groups, okay? And get a little bit comfortable with what this is. I guess the easiest examples are, of course, finite groups. So these are examples, right? So every finite group has a finite presentation because you can write out the multiplication table presentation, right? You take any two elements, x times y, and you write xy equals the product of xy. That's another element, right? And you express that as a relation, or you have to use an inverse to express it properly. Free abelian groups, I think, is another notable example, right? So this is, I think, famous. Every subgroup of a free abelian group is, again, free abelian, right? And free abelian groups are finitely presented, right? You know how to write out the presentations. And a little bit fancier, I'm going to start to write finitely generated, FG for finitely generated, nilpotent groups. A little more general still, polycyclic groups. Nilpotent groups, you have a group and you kill the center, and then you look at what you get, you kill its center, and you keep doing that, and if you eventually reach trivial group, you were nilpotent. And polycyclic group, these are kind of generalizations of, again, free abelian groups. These are groups that have, what are those called? Normal series where all of the all the factors are cyclic. That's one way of saying what that is. This is probably, yeah, excuse me?
You erase finally degenerated would be right?
Well, yeah, it would be right
Okay.
if you erase it. Okay? Yeah, because it's only about finally generated.
Yeah, we're in the
It's only about finally generated subgroups. It's just it's just words that came out of my mouth. Thank you. So, these are not the types of groups I'm interested in. And let's kind of, although I'll have some comments to make about these, in a way, these are all also trivially coherent. They really are. You get them from the definition, you play around a little bit, and you can see that it's true. The ones that I'm more interested in are a longer list. I'll just put a few examples now.
Excuse me. Could you
Yes.
give a simple example of a non-coherent?
Well, of course.
Coherent.
Of course, I'll do that soon. Okay? So it's a good comment that there are groups that are not coherent. Okay? So I'll give examples here. So here I'll put one down over here. Okay? Just to reassure you that they're out there. Okay, so that's the direct product of two free groups of rank 2, which is a group you've thought of before. Okay, so it is not coherent. Okay, and I'll continue the discussion, and then maybe we'll talk about that a little bit. So, free groups are coherent, and what's the comment that we make about it? It's a famous and beautiful fact that subgroups of free groups are again free. Okay, so that's why they're coherent. Surface groups. This is getting a little bit more geometric. By a surface group, I mean, the fundamental group of a surface. Okay, so we saw one example, a torus, but it's true for any surface, right? And the non-interesting surfaces are the sphere and the projective plane. We already covered those. And then the first really deep theorem is three-manifold groups. Meaning the fundamental group of any three-dimensional manifold. And this is Scott and independently Shalin. Building on a work of Swarup and using classical three-manifold topology ideas. Okay, and not an obvious, neither obvious nor immediately easy to prove from the definitions. You have to work. And you have to. It took many years until people understood why this was true. Now, this is. I always forget. Maybe it's about 78. I think that's probably about right. A little bit. So it's worth commenting actually that. Well, this is a subgroup of the fundamental group of a four-manifold, right? Because it lives inside of, just to continue the conversation on this blackboard, a free group lives inside of a surface group. Here's a four-manifold over here, right? So we didn't even have to bother saying that every finitely presented group is isomorphic to the fundamental group of a four-manifold. We see immediately that there are four manifolds whose fundamental groups are not coherent. Okay, so it's good that you got me going over there. Let's continue a little bit more, just to give a little bit of a sense of what's happening here. Around 99 or so, there were two other works. The more important one, I think, is free by cyclic groups, and actually a little bit more general than that. This is Fein and Handel. What do I mean by free bicyclic? I mean, if you take a short exact sequence, where the normal subgroup is free and the quotient subgroup is cyclic, this is the free bicyclic group. Okay? And Fein and Handel proved that free bicyclic groups are coherent. That is a very, very large class of groups, right? And it's interesting to, I was having fun yesterday asking what you thought, more residual finite groups or more torsion. What do you think? Are there more three-manifold groups or more free bicyclic groups? Which is a richer class? Am I allowed to do that in these talks? Huh? With actual adults?
I don't know.
Totally wrong. What? Huh? Who else has a guess?
You, there's only one.
Three manifolds are virtually fibered by circles. So is that what you mean?
I think that, well, I mean, it's two infinite classes, right? Of course, this is a much richer class, and in a way, if you know virtual fibering for the three manifolds, it actually follows from the free bicyclic case, which is amusing. Okay, that doesn't prove anything. It's just something to have a conversation about. It's like, some people like arguing about sports teams, right? This is what I like to talk about. Okay, I think it's much more interesting. In fact, they proved a little bit more than that. They proved that if you have an ascending H&N extension of a free group, then it is coherent. So what does that mean? I'll write it over here. Ascending H&N of a free group is coherent. So what that means is you might take a monomorphism from F to itself, and then you form a group which is given by, let me write it out like this. Maybe our free group will be on, I don't know, A and B, just for simplicity. You add what's called a stable letter, T, and then you say that A conjugated by T is equal to phi of A, and B conjugated by T is equal to phi of B. For instance, this is the two-generator case. It could have been an infinite, F could have been an infinitely generated free group as well. It works the same way, right? And we're not using that phi is an automorphism of F, just that it's a monomorphism. And they actually prove this, okay, which is quite a bit more general than free bicyclic, okay?
Sorry, F here is just
a free group. F is a free group. F is the free group. Over here, F equals the free group on A and B, just for an example to illustrate.
What makes this ascending? In what sense is this ascending?
What makes it ascending is that some people would call it descending, okay? And it just means that when you conjugate F by T, you're mapping F into itself. So then you would want to conjugate again. You're mapping it further into itself and further into itself and further into itself. Okay? So that's the language. Probably people like to call it descending. It's just some people like conjugating by T inverse instead of T. Okay? Okay, I have no idea.
F is always contained in this new
I'm saying it again.
F is always a subgroup of this.
F is, yeah, this is, so that's a, so H and N is a sort of jargon, unfortunately. It's Higman, Neumann. It's a, it's the, for topologists, it's the analog of an amalgamated free product. So the amalgamated free product is when you, is the disconnecting case, and there's also a non-separating case, and that's the H and N extension. But it's a, it's not our topic. Okay? Sorry about that. But I told you what it meant. Okay. Now, interesting to comment. Is it? I forget the names. Is it Groves? Maybe Strabel. Berry. Showed that for solvable groups, they show that coherent solvable, like we mentioned nilpotent, but we left out solvable, which doesn't get treated very nicely. Coherent solvable groups are precisely ascending HNN extensions of polycyclic. Cyclic, I left out a Y. I'll just put the Y over here, okay? Polycyclic, I don't know, polycyclic, yeah, there's a Y. And I left out a C, I'll put it here. Groups.
So it seems natural to guess that an ascending HNN of any coherent is.
That is reasonable guess, okay? I don't think that's true, but it's a reasonable guess, okay? And in some sense, so this is I don't know, let's say about 85. In some sense, it kind of completes a picture to a certain extent of what you might call small. These are small groups, and here I'm writing out a collection. I'll say sort of small. Here I'll say sparse. They're free-ish. They don't have that many relations. So let's write out around the same time, McCammond and myself. We sorted out what you might call perimeter groups. For avoid getting into why we would call them that. And let me just give one suggestion of what we did. If you take a bunch of, if you take a presentation and you take a bunch of generators, a bunch of relators, excuse me, and you assume that those relators have nothing to do with each other. No two of them have conjugate powers, for instance, conjugate non-trivial powers. Okay, so they're independent in some sense. We showed that there exists n, depending on this initial data, such that such that we obtain such that coherence holds when you raise them to large exponents greater than or equal to capital N. So N1, N2, N3, and S. Huh? And it's for people who are not group theorists, you'd think that raising words to powers is making your group harder and more difficult, but it's actually the opposite that happens. The way group theory works, infinite group theory, the way it works, if you raise your relator to large proper powers, you actually are making your group easier to understand because you're making it more sparse. Okay, that's all that's
So
happening
the
here.
statement is if there is such an n for which the group is coherent, then the original one is coherent?
No, the statement is that no matter what words you choose, as long as they're all different from each other, you can always, there exists some number n, so that as long as you raise them all to powers that are at least that big, coherence kicks in.
Yeah.
What's your question?
That's amazing. For F2 cross F2, it works as well?
Well, you mean, so for F2 cross F2, so for example, so for example, if you have A, B, C, and D, right? And
A commutes with C and D.
yeah, let's do that. A, B, A inverse, B inverse, A. I'm not doing so well over here, right?
Yeah, okay.
Huh? I'm not doing well. Let's do it.
It's okay.
It depends, but we all knew. So let's just fix this so that to make it a little more organized. A, B, and X, Y. Okay? And then A commutes with X, so let's write A, X, A inverse, X inverse, A, Y, A inverse, Y inverse, B, X, B inverse, X inverse, B, Y, B inverse, Y inverse. And the question might be, what powers make it coherent?
Yeah.
I have not thought about this, or if I have, I've already forgotten about it. Does it work at the 10th power? Yes. Yeah, for sure. We could stop and and destroy the talk, and I could work out and and check to be sure. I would say, I'd now bet. I bet. Does it work at 3? I'd say probably. Does it work at 2? I want to stop the talk and think about it. Okay? But I'll tell you my secret method for knowing what's true and what's not. I will show you everything, but I have to move forward. Yeah? And then you'll know how to think about this. Okay? Okay. Maybe I'll mention one more. Negative sectional curvature. All right, so this is just an example of how to use perimeter, whatever that is, in order to prove coherence. Okay? Negative sectional curvature, you've heard of non-positively curved spaces? Yes, no? Yes, no, yes, a little bit. Yeah? So I'll give one example that responds to non-positively curved spaces, okay? So here's another class from around the same time, maybe 2 years later. So it's about 2001. If X is a two-dimensional complex such that the universal cover of X is, I'll say cat 0, but actually, let's say cat minus 1. So it's a negatively curved space, right? And X locally embeds in R3, right? That's not usually the way I say it to myself. Rather, I say equivalently, the link of every 0 cell of X embeds in the plane. Okay, it has, I like to say, spherical links. Then pi 1 of X is coherent. Strange statement. Okay? So there's something close to the three-manifold about this. It's very different from three manifolds, of course. These are not being locally embedded. A two-complex being locally embedded in R3 doesn't mean you can thicken it up to being a three-manifold. It doesn't have, it's not a deformation retract of a three-manifold. No. There's globally, it could be problematic. That's very interesting. Okay. Well, this is a good example to mention F2 cross F2, right? Which is not coherent. So it's a two complex. It's cat zero, so it's almost, you might say, it's non-positively curved at least. What does the link look like? What is the link? So this is a two complex over here, right? It's built from squares. The link of the 1, 0 cell is isomorphic to the complete bipartite graph on 4 and 4. I'm not even going to try to embed it. Right? And if you're more efficient, of course, you could think of this as the fundamental group of the product of these two graphs, right? And now the link is actually going to be K33. So there's opposition over here, okay? I will engage with F2 cross F2, so to reassure you that there are incoherent groups. There are many, and then I'll give you sort of thoughts about what's going on over here. So since we're talking about F2 cross F2 already, there's a homomorphism. We'll use A, B, X, and Y. There's a homomorphism from F2 cross F2 to the infinite cyclic group that sends each of its generators to, unfortunately written as, maybe we'll, it sends each of them to 1. Okay, you could deal with that. Okay, it sends each of the generators of F2 cross F2 to the generator of the infinite cyclic group. And the kernel N of this homomorphism is finitely generated, but not finitely presentable. It's not finitely presented. Okay, so this is a one really beautiful example of a business of John Stallings, Berry, and then Bestvina Brady. This is, I don't know, even John must have done it in the about, I'll say 80. I should double check if it might have been a lot earlier. Maybe 70s. Baumslag was doing some things also that were close to it. Berry was doing this in the 80s. Actually, Berry was looking at arbitrary products of, say, free groups, and looking at the kernels and studying not just the two-dimensional finiteness properties, but higher finiteness properties. And he gave magnificent work on this that was very influential. And Bestvina Brady, 1995, 96, around, gave an extremely influential generalization of this entire business over here, with beautiful and elegant conditions that will let you see finiteness properties of the kernel, and so you might be able to see that the kernel is finitely generated, right? It's the simplest finiteness property you might care about, and also maybe in some other fashion see that it's not finitely presentable. Usually the way people show things are not finitely presented is they compute homology. That's the usual way. They compute the homology and show that the homology is infinitely, if you have a finitely generated group, if you manage to show that the homology is infinitely generated, you're not finitely presentable, right? So in response to are there any non-coherent groups, the real response is, yeah, most groups are not coherent because most groups are finitely generated. There are only countably many finitely presented groups. Most groups are, most two-generator groups, almost all of them are infinitely presented because you take two generators and you take a random crazy set of relators. It's not finitely presentable. That's what usually happens. Okay? So I think that's the real answer to are there any non-coherent groups, right? But the real question wasn't that. The real question was, okay, were there any reasonable groups which are, of course, finitely presented because they're reasonable, but which are still not coherent, right? Why are we interested in this anyway? For me, I'm interested in the magic of presentations where you put a little small finite amount of information with a few generators and a few relators, and you see this incredible phenomenon that we encounter in mathematics where a small amount of information can lead to a crazy chaotic situation. Right? We just can't believe how complicated it gets from just some simple rules, right? And the possibility of having a finitely generated subgroup inside, right? That's your group was a nice finite amount of information. Here it is, and then you take a few generators, and then you, in a mesmerizing fashion, you have a crazy amount of relations that might hold, and it's out of control. And we like that because it makes us, on the one hand, helpless. But on the other hand, powerful because we're custodians over a complicated business. Okay, so we know a little bit about it, even then we also know that we don't really understand it so well. Okay, I better get back to my talk instead of blabbing a bit. So there are lots of non-coherent groups. Maybe I'll mention one more. There are non-coherent groups with just two relators even. There are examples of groups with two generators and two relators that are not coherent. So I think Thompson's group is one. I made up my own examples, back when I started thinking about this in the around 2000 or so. Rips gave some of the first important examples using his short exact, Rips's short exact sequence, if you've heard of that. Let's now philosophize a little bit about the picture over here.
Are all one?
Yes, they are. So let's philosophize that, and let's see what's what is going on here. I philosophized about it around that time, around 2001, and tried to say, what is it that's going on over here? What do the coherent things have in common with each other? And what I found was the following. I found the following notion: a 2 complex X has non-positive immersions. If any immersion, I'll remind you what that is in a moment, y to x with y compact and connected, satisfies either the Euler characteristic of y is less than or equal to 0, or there's different ways of saying this. Let's say pi 1 of y is trivial. Okay, so what is an immersion? An immersion is a, well, we're working in the category of two complexes actually, so it's a combinatorial map, meaning 0 cells are sent to 0 cells, 1 cells are sent to 1 cells, 2 cells are sent to 2 cells. Okay, no tricks. That is a local injection. Okay? So, to know a definition, you can't just memorize the definition, you gotta experience it a little bit. Let's prove that some two complexes have this non-positive immersion property so that we can grab a hold of the definition. So, the easiest two complexes are probably one complexes. Okay? Graphs, any one complex has non-positive immersions. Why is that true? Well, if you have a complex that immerses in a graph, it was a graph. And the Euler characteristic of a connected graph is always non-positive unless it's a tree, in which case its fundamental group is trivial. So graphs have non-positive immersions. What about any surface except for a projective plane? Okay? So let's think about that. And I'll spill the beans and I'll tell you it has non-positive immersions. So let's say you have something immersed in a surface. What does it look like? Well, if you're flexible, we can write out a careful proof, but it's better to be flexible. This thing which is immersed inside of a surface, you could thicken it up slightly. And that doesn't change its nature, it doesn't change its homotopy type, right? And now, whatever it was, it became a surface, right? Maybe it was already a covering space, right? If it was a covering space, then you're looking at a covering space of a surface. It's again a surface, and Euler characteristic is multiplicative on degree of the cover, so you're okay. Okay, but let's think about the more general case. You have something that was kind of a little bit nasty immersing inside of the surface. You thicken it up slightly, and it has the same homotopy type as a surface with boundary immersing inside of the surface. And a surface with boundary, deformation retracts to a graph. A surface with boundary deformation retracts to a graph. You just start collapsing the boundary inwards. And graphs, we know, are all either trees or they have non-positive Euler characteristic. So any surface has non-positive immersions. And actually, you can prove that any three-manifold with any irreducible three-manifold, I should say, but whatever, with boundary has a spine with non-positive immersions, meaning that there's a two complex inside of this three manifold. You can deformation retract the three manifold to this two complex. And this 2 complex that's inside, which has the same fundamental group as it, has non-positive emergence. So this is a little harder. These I really sketched these out. This is a little bit harder. Okay. And actually, Fein and Handel, I mean, there's a natural 2 complex associated to an ascending H&N extension. What you do is you look at your map phi, and you sort of form what's called a mapping torus associated to phi, right? Maybe A and B, perhaps A went to, for example, AB, and B went to, I don't know, B, A, B, for example. So AB and B, A, B, and this so-called stable letter, I put it right over here. Here's T. And I create a 2 complex that is associated, actually, it's just the standard 2 complex of this presentation. Actually, I should have just said that. Okay, it's just the standard 2 complex of this presentation. So there's a 2 cell for this and a 2 cell for that. Here's just a picture of it. I didn't realize I had it on the blackboard already without any pictures. Okay, so you kind of form this 2 complex, which is associated to your endomorphism from F to itself. So there's this 2 complex that's associated to the ascending H&N extension of Fein and Handel. And it's an easy computation to see that it also has non-positive emergence. Any, let's just call it a free by Z 2 complex has non-positive emergence. This is easy, as it's easier than this. This is a little bit easy, a little bit hard, because it depends on other people's, it depends on some things that are not so obvious. This is easy, an easy computation, actually. Okay? I mean, it would still be unpleasant to go through it, but it's easy. It's routine. And what so I kind of sat and thought about what was going on over here, and also these also have non-positive emergence, and these also have non-positive emergence if you play some games with the numbers. Never mind. Okay, cheat slightly, and I reached the conclusion that non-positive emergence was the thing. So I was led to the following. The following guess that if the 2 complex X has non-positive emergence, then the fundamental group of X is coherent. Also from around 2001 or so. Just kind of like some type of hope to find the common denominator. I don't know if math works that way, but humans work that way. And well, even more, a little bit bolder. I don't know if I'd call them conjectures, or it depended on the day. Conjectures or problems or questions. That if G is coherent, and the cohomological dimension of G is 2, then G is equal to pi 1 of x where X has non-positive emergence. So that somehow, this would be too good to be true, of course. Somehow maybe coherence is intimately tied up with this non-positive emergence for two-dimensional groups. I should say, coherence it's kind of a 2 or 3-dimensional phenomenon. It's really a 2-dimensional phenomenon. It's not even a 3-dimensional phenomenon. Okay, all of the examples that I've been showing you are essentially 2-dimensional. This is, there's torsion over here, but anyway, you can get rid of the torsion, or you could think of it as a group acting on a 2-dimensional space with some finite stabilizers. So it's not a big deal. Okay, these are all basically 2-dimensional examples. The 3-dimensionality, right? This would make you think, oh, this is a 3-dimensional phenomenon. It's not true. It's a 2-dimensional phenomenon. It's because anyway, the subgroups of a 3-manifold group, the finite index ones are again 3-manifold, right? But of course, a finite index subgroup of a finally presented group is finally presented. Nobody's interested in those subgroups. Those are obvious. It's the infinitely presented subgroups that we're interested in. It's the infinite index subgroups, excuse me, that we're interested in. And those are 2-dimensional, actually, from the for a spherical 3-manifolds. Okay? And, okay, well, you got me. Zn. Z4 is 4-dimensional. Okay? This is a high-dimensional phenomenon. Coherence works in high dimensions. But it isn't really like that.
Pretty special.
It isn't like that. Those are small groups. And what is happening actually is that there is a theorem. There is a theorem that old style combinatorial group theorist business theorem that says that if maybe it's Karras and Solitar should be attributed to those guys working in the 60s. If G splits as a graph of groups, let's say just as but I'll say as an amalgamated product, but I mean a graph of groups. I'll write an amalgamated product just to keep it a little more real. Where A and B are coherent, and the amalgamated subgroup C is Noetherian. All of its subgroups are finitely generated. It doesn't have any infinitely generated subgroups. Then G is itself coherent. And there's a version of this for graphs of groups as well.
So graphs of groups is just like the right-angled Arden monoids where you replace every vertex with a group. And
no, graphs of groups are first of all, you have your L over here, and she could tell you all about it.
Okay.
Okay, when I'm gone. Okay, right? Yeah. So what a graph of groups is you you take a bunch of spaces and you take a space and you kind of cut it up into pieces. Here I've broken my space up into kind of has a little architecture over here, a little blueprint for it. Here was my whole space, and I've broken it up into kind of 3 vertex spaces and 2, 3 edge spaces by coincidence. And if each of the edge spaces pi1 injects inside of the whole thing, then that allows you to split the fundamental group of this space into what's called a graph of groups. And there's a very nice theory that was, combinatorial group theory of the 50s, 60s that then Serre made into trees. And it corresponds to a way of thinking of the group acting on a tree in a certain way. You've heard of this. And the splitting case just corresponds to an amalgamated product. That's this case. But it works in general. And the so-called H&N extension that I mentioned over here, that's actually this case over here. That's the case which is kind of in analogy to the amalgamated free product case. That's the case where the edge space doesn't separate the whole thing. Okay, that's why these are kind of in alliance with each other. This is a general graph.
So if you could present a group by a graph of coherent groups, it's good.
Very almost. As long as the edge groups are very small, they're Noetherian. And because of this theorem, which is a pretty easy theorem, okay, because of this theorem, you can, take more and more splittings of groups where you're splitting over this nice Noetherian group, or these are all Noetherian over here. Those are all Noetherian, okay, and so because of that, you can build more and more coherent groups by starting with basic building blocks that you might have obtained from here, or that you might have obtained from here. And you can create 7-dimensional and 13-dimensional groups with a trick, where the cohomological dimension going up is because of smallness, not because of sparseness. Okay, so as it stands right now, there are no known examples of coherent groups which do not fit into this vision that I'm telling you about, where they're basically they belong in this non-positive immersion category, or can be built, Okay.
So like a coherent by Z extension.
Coherent by Z, I think that you could find non-examples. Okay, so. Although I have to stop and think about, I'd have to stop and collect my thoughts on that. Okay? Huh?
Just how this is not a subcase of Z is Noetherian.
Z is Noetherian. So, for instance, a surface group can be thought of. So one of the favorite ways of thinking of the fundamental group of this surface over here. You're cutting it along this cyclic subgroup over here, and you break it up into a free group on the left and a free group on the right. And now you have a coherent group, a free group, and another coherent group, a free group, amalgamated along a cyclic subgroup. So the surface group is coherent. That's another way of saying that the surface group is coherent. Because the Fein and Handel situation, I erased it. The Fein and Handel situation. I'll redraw it over here. When you break it up, the thing that you're cutting along is actually a free group. Right. And free groups are not Noetherian. They have infinitely generated subgroups.
Okay.
Right? Now,
the C is not.
when you think of this free bicyclic group, even though you see the cyclic group is not what you're cutting along to build the free bicyclic group. You're cutting along a free group. You're forming what's called an H&N extension along a free subgroup, not along a cyclic subgroup. Okay? What would work for a free group would be something like taking a graph, a free group, and then gluing a cylinder onto it and forming this topological space and looking at its fundamental group, And now you'd say, okay, the vertex group is free and the edge group is cyclic, so it's Noetherian, so it's coherent. Okay. Well, what was I after when I was cooking up this definition? I was after the following problem of Baumslag. His conjecture was any one relator group is coherent. This is Baumslag. And what I imagined was that how are we going to tackle this problem? Just two simple things. Show that whenever you have a one relator 2 complex, right? So you just take a one relator 2 complex, you take a vertex, you take 2 1 cells, and then you add 1 2 cell to it. Glue it on. Prove that this has non-positive emergence. It's a very simple type of 2 complex. Prove that it has non-positive emergence. Step 1. Step 2, prove that if you have non-positive emergence, then you're coherent. That's the, large language models can't do that yet, but they will soon. But I'm a human. I kind of said, okay, here's my plan. And I feel very natural telling you about this in Israel because I spent so much time worrying about why this had non-positive emergence in Israel, actually, in particular. This I proved. This one I did in a hotel on Yefei Nof. Actually, I remember it very well, listening to a soccer game broadcast in Arabic. So this is made in Haifa. This I spent God knows how much time in Jerusalem thinking about it. I thought this would be easy. It took about 15 years until it was understood. So in fact, it has non-positive emergence. This is Lauder. Wilton, I particularly encourage people interested in this to look at their amazing, beautiful gem of a proof. It's a gorgeous proof. And Helfer and myself, we did it around the same time, about 2015. Showed that it had non-positive emergence. The proofs look different to begin with. We used that one related groups without torsion are left orderable. They used that they are right orderable. Okay, so those are different. I mean, they're equivalent, but they're different. They were motivated maybe by work of Howie, perhaps. I'm not sure. We were motivated by Dick's Meneev proof of the Anna-Neumann conjecture, that this was somehow the rank 1 version of it. Okay, so it was connected to interesting things. If you might have heard of this. There was a thing called the Anna-Neumann conjecture, which was resisted people for 50, 60 years until it was figured out by Friedman and Meneev independently. So as soon as that happened, then we were able to do it. And very recently, Linton and sorry. I have the HIJKL, whatever. You can forgive me. Not sure what to do with these Spanish names. How about that? Marco Linton and Chaikin Zapiren proved that if G has non-positive immersions and one more thing, G has a hierarchy, then G is coherent.
Is that in CD equals 2?
So a hierarchy means that that you can build the group by repeatedly performing amalgamated free products and H&N extensions. So you should just think of it as you can build the group by starting with, say, cyclic groups and doing an amalgamated free product, and then doing another amalgamated free product, and then keep building more and more groups using just amalgamated free products.
There's no CD cohomological dimension?
No, it's no, but there's all sorts of properties that you can collect from non-positive immersions, and there's a slightly different version of this, which is usually I like to say, or Y is contractible. And if that's the case, then X has, this is what we usually do in practice. Not that pi1 of Y is trivial. We actually have a stronger hypothesis, stronger conclusion. Either the Euler characteristic is non-positive or Y is contractible. In that case, what you do is you get that X is aspherical, and so the cohomological dimension is 2. I mean, there's a whole industry now that is starting to develop around this. There's many different variations of this definition. So the corollary is that Baumschlag's conjecture is true. It's a fantastic theorem. Give it 3 checks. One-related groups have hierarchies. It's the primary method for studying a one-related group is that you can build a one-related group by taking an H&N extension of an H&N extension of an H&N extension of an H&N extension. This is essentially in Magnus's PhD thesis. Okay, and so we win, right? We collect Baumschlag's group as being coherent. Let's stop now. Thank you very much.